In this video, we will continue our discussion of antiderivatives, and we'll talk about their relationship to something called differential equations. Now, what is a differential equation? Let's write down the definition. A differential equation, or as it's usually abbreviated, a DE, is any equation involving one or more derivatives. So that's what a differential equation is. Let's give a very simple example. Find a function, let's call it capital F, for which f prime of x is equal to, let's say, 3x squared plus 4x cubed. All right, here we're looking at a differential equation right here. This is an equation that involves a derivative of the function capital F. So we have our differential equation, and our goal here is to find some function f which satisfies that differential equation. We call that a solution. So we want to find a solution to the differential equation. How do we go about that? Well, in this case, really, we're being asked to find the antiderivative. We're given a function 3x squared plus 4x cubed, and we want to know an antiderivative for that. We want to know a capital F so that the derivative of that is 3x squared plus 4x cubed. So let's proceed. So solution. We can do this term by term, as we say. We have 3x squared plus 4x cubed, 3x squared plus 4x cubed, and we want to find the antiderivative of this sum, so we can find the antiderivative of each individual term and add them together. I say the antiderivative, but really there isn't one antiderivative. There are, of course, infinitely many. So let's proceed by doing it that way. Let's find the general antiderivative. So we're looking for capital F at x. So it's the antiderivative of 3x squared, which is 3 times the antiderivative of x squared, which is a power function. So we use our reverse power rule. We increase the exponent by 1 and then divide by that new exponent. Plus, and now we want to find the antiderivative of 4x cubed, and the way that we do that, again, is it's 4 times the antiderivative of just the x cubed term. And again, we use our power rule, or our reverse power rule if you prefer. So we increase the exponent by 1 and divide by that new exponent. Now this is one antiderivative. If we want the whole family of antiderivatives, we just add in plus capital C, where C is an arbitrary constant. Now this can simplify because our 3's can cancel and our 4's can cancel, and that will leave us with x cubed plus x to the fourth plus a constant. So this is the general antiderivative. That's the general antiderivative. All right, so we were asked in this problem to find a function for which f prime was equal to 3x squared plus 4x cubed. What we actually found were infinitely many. These are what we call solutions to the differential equation. A solution to a differential equation is a function which makes the differential equation true. And here we have infinitely many. Now, if we want to specify a specific antiderivative, we need to find a value for capital C. And in order to do that, we need some additional information. We need what's called an initial condition. So an initial condition for the differential equation f prime, capital F prime at x equals little f of x is an additional piece of information, is a condition of the form capital F at some value x0 equals some output value y0. This is what we call an initial condition. It's some additional piece of information. It tells you what value f has at some point. In this case, we're calling it x0. So we can use this initial condition, or we can use an initial condition to determine the value of c. So let's return to our example. Let's look at the same example, but now find the unique function capital F for which we're going to have the same derivative here, the same differential equation. So it's f prime of x equals 3x squared plus 4x cubed, but we're going to have some extra initial condition. And let's say f of 1 equals 4, just to keep things simple. Right? Now this additional piece of information is our initial condition. Now just like with differential equation we often abbreviate it as DE, initial condition we often abbreviate as IC. So let me just put that here, IC. So what we want to do is find the unique function f, which has the same differential equation as we had before, but now it also must satisfy this additional initial condition. So what's the solution going to be? Well, we already know, so we know that capital F of x is going to be equal to x cubed plus x to the 4 plus c for some value of c. We just need to figure out what value that c is. And for that, we use our initial condition. So we know that f of 1 is equal to 4. So what that means is we plug in x equals 1 into our function there, and whatever that output is, it needs to be equal to 4. So let's just go ahead and do that. F of 1 is equal to 1 cubed plus 1 to the 4 plus c. And whatever that is, it needs to be equal to 4. Well, of course, 1 cubed is 1, plus 1 to the 4th is 1, plus c is equal to 4. Well, 1 plus 1 is, of course, 2. So what does that tell us? That tells us that c is equal to 2. All right, so now we know that capital F of x is equal to x cubed plus x to the 4 plus 2. And this is our solution. This is our unique solution to the differential equation subject to the initial condition, as we say. Now, what does this initial condition really tell us? So let me just write this as a remark. F of 2, not f of 2, f of 1 equals 4 means that the point where x is equal to 1 and y is equal to 4 is on the graph y equals f of x. Okay? X equals 1, y equals 4, that is what we write as 1 comma 4. So an initial condition is really telling us the value of the x value and the y value of a point on the graph of the function. Let's take a look at the graph of this particular function. So here we have the graph of y equals x cubed plus x to the fourth plus 2. So you can see in the upper left that I have plus c, where c is equal to 2. This is the graph. And if I just make it a little bit bigger, you can see here that where x is equal to 1 and y equals 4, that's a point that passes through the graph. If I change the value of c, that will change the location of the graph on the xy plane. It will translate it either up or down depending on whether c is positive or negative. So for example, we can slide through different values of c, and you can see what happens is the graph moves up or down. We're just translating it up or down. Different values of c give you different locations on the graph. So by specifying a certain value of c, for example, if we specify that c is equal to 2, that tells us exactly where we are on the xy plane, and you can see that we have x is equal to 1 and y equals 4 is a point on the graph. All right. So the initial condition is precisely a point on the graph. All right. Now, a collection of a differential equation together with an initial condition will give you a unique solution as long as your function is continuous. Now, there's a special name for this sort of thing, so let's call this another definition. So a differential equation together with an initial condition is called an initial value problem. Now, naturally, this is also abbreviated. We call it IVP, initial value problem. So what we can say is that an initial value problem is a differential equation together with an initial condition. And an initial value problem will have a unique solution provided that your function is continuous. So we can make a theorem to that effect. And the theorem says that if f is a continuous function, then the initial value problem f prime of x equals little f of x with some initial condition f at x0 equals y0 has a unique continuous solution. A unique continuous solution. That's important. Now we see that example in our example. We had a continuous function and it had a unique continuous antiderivative that satisfied the initial condition. The continuity is important because that's what forces the uniqueness. Let me give you another example. Find an antiderivative for f at x equals 1 over x such that capital F of 1 is equal to 3. Okay. Now, I haven't given the domain here, so solution if we restrict our domain to positive values of x, so let's say the interval from 0 to infinity, so that's just x strictly greater than 0, then this initial value problem has a unique solution. And we can actually write it down. Capital F of x is equal to the natural logarithm of x plus some constant. Now, in this particular case, that constant's going to be 3. We know that f prime of x is equal to 1 over x, and f of 1 is equal to ln of 1, which is 0, plus 3. So you can see that it has a solution, that this is a solution to the initial value problem. Now, this is only true if we restrict our domain. Notice I didn't have absolute values around my x's because I was assuming that x was greater than 0, so x was positive. If I remove that restriction, that changes the problem considerably. So if we assume only that x doesn't equal 0, then we lose our uniqueness of solutions. Why is that? Well, our function here is discontinuous at 0, so we're allowed to have some kind of jump. Now, what do I mean? Well, here's an example of a solution. So, example of a solution. I could let capital F be piecewise defined so that it's ln of x plus 3 if x is greater than 0, and ln of minus x plus any constant I want if x is less than 0. Now, this is not one function, so I shouldn't say example of a solution unless I say for any value of c, you'll have a solution. Okay. Why is that? Because I know that f prime of x is equal to, well, it depends on if x is greater than 0 or less than 0, or at least it seems like it would at first. Now, if x is greater than 0, then we differentiate ln of x plus 3, and we end up with 1 over x. Now, if x is less than 0, then we need to differentiate ln of minus x, but we did that before, and we know that that's also 1 over x. So we see that f prime of x is equal to 1 over x for all x not equal to 0. So this does satisfy the differential equation that we started with. All right? But also it satisfies the initial condition. F of 1 is equal to, well, since we're looking at x equals 1, and that's positive, we're now looking at the top condition. So we're looking at ln of 1 plus 3, which is 0 plus 3 equals 3. So it satisfies the initial condition. But that doesn't affect the bottom condition here in our list of rules defining capital F. Our initial condition told us about this rule, ln of x plus 3, but it doesn't tell us anything about our bottom rule, because this bottom rule is different. It only depends on x values that are less than 0. So there's no communication between x values greater than 0 and x values less than 0. So on the interval where x is greater than 0, you have a continuous function. So knowing your initial value pins down that constant to plus 3. However, it doesn't tell you anything about the x values that are less than 0, because our initial condition was for x equals 1, which is greater than 0. So that doesn't tell us anything about this rule in the bottom here. So it doesn't tell us what the value of C is. Any value of C will do the job. So what we've effectively done is lost our uniqueness. All right. So I think that that's a good place to stop this video, and we'll resume with an example of a differential equation for equations, what we call equations of motion.